This is a continuation of the previous lecture where we were discussing projective and quasi-projective varieties. So the last thing that we saw was that if you have a projective variety, then there are no non-constant global regular functions, and as corollaries we saw that the only morphisms from a projective variety to an affine variety are the constant maps, and putting the condition of projectiveness and affineness on a variety reduces it to a point. Okay, these are all just reflections of the fact that there are no non-constant global regular functions on a projective variety. Okay, and therefore one line of thought from this is that if one still goes by the philosophy of Felix Klein that the geometry of a space is controlled by the functions on it, then it is very clear that the geometry of a projective variety cannot be controlled by just looking at the global regular functions, because there aren't any non-constant of global regular functions, and therefore you will have to concentrate on regular functions on open subsets of the projective variety, and this leads to what is called as birational geometry, and that is studying the geometry of open subsets. Okay, and therefore the clue is that if you cannot keep track of the geometry of the projective variety by looking at its global regular functions, which are only constants, you can still keep track of the geometry of the projective variety by looking at regular functions on various open sets. Okay, and this is covered by studying sections of line bundles on a projective variety, and this is something that you would see in a second course in algebraic geometry. Okay, so I'm just trying to say that the statement of Felix Klein, the philosophy of Felix Klein, that the geometry is controlled by the functions, still applies also in the case of a projective variety. Only thing is that it's not enough to just consider global functions because they are only constants. You have to consider functions on open sets. Okay, and the device that which keeps track, attaches to every open set the regular functions on that open set, is what is called the sheaf of regular functions. Okay, so one needs to keep track of this using sheaf theory, right, which most probably you would see in a second course in algebraic geometry. So now what I want to do, I want to I just want to continue saying the following, that so basically I want to go back to our earlier argument where in I think a couple of lectures ago, where I showed that the projective n space was a union of n+1 copies of a finite space. So so let's recall that. So you see we have projective n space, and we of course take the homogeneous coordinate ring for the projective n space as k x0 through xn, and these xi's are the coordinates on the affine space above the projective space. So you must remember that there is an a n plus 1 minus the origin, of which the projective space is a quotient by this quotient map, which is quotient by the equivalence relation that identifies all points on a line passing through the origin in the affine space above, and the coordinates here are the xi's, and the corresponding coordinates here are called homogeneous coordinates, because here only the ratios are the coordinates are ratios. And now you look at the set ui, where ui is the projective space minus the 0 set of xi in the projective space. Notice that each xi is homogeneous of degree 1, therefore its 0 set is a closed subset of projective space. It's called a hyperplane because it corresponds to the ith coordinate being 0, and its complement is this open set ui. This consists of all points with homogeneous coordinates with ith with the subscript I coordinate non-zero. Okay, and then I told you that there is a map phi from an to ui, and I would ask one of you to check whether phi was defined in this direction or the other. Was this the map phi or was it the other way around? Okay, so it was the other way around. So let me, so that I stick to the notation I started with earlier, and this map was very simple. What you did was you took a point with coordinates lambda naught etc lambda n and simply send it to the point lambda naught by lambda 1 lambda I dot lambda n by lambda I, where of course omit lambda I by lambda I. Okay, so this is the map we defined, and we checked, it's easy to check that this map is a bijective map. Okay, and I asked you to check that this map is actually a homeomorphism of topological spaces, and so you know, so what I want to say now is that suppose I start with the topology on the projective space given by the quotient topology for this map, with the topology above being this one induced by the Zariski topology in affine space. Then this topology with Pn with that topology will induce a topology on the ui, and for that topology phi is a homeomorphism with an having the usual Zariski topology. So so the way this is interpreted is that if you want to give the topology on Pn, there are three ways of doing it. One is you define the closed sets as 0 sets of a bunch of homogeneous polynomials. Then the other way is by giving the Pn the quotient topology via this quotient map. The third way is that you make each of the phi's homeomorphism, namely you transport on you give the topology on ui that makes this a homeomorphism, namely a set here is open or closed if and only if its image here is open or closed, and then these topologies on the individual ui's will agree well on the intersections, and therefore they will define a global topology on the projective space, and that will be the same as the quotient topology or the topology for which closed sets are given by 0 sets of a bunch of homogeneous polynomials. Okay, so all these are the same. So to you know now to make things more clearer, in fact what I want to say is that these phi are not they are not just homeomorphisms. These phi's are actually isomorphisms of varieties. Okay, so fact each phi is an isomorphism of varieties. Okay, and Yeah, okay, this is not equal, I am sorry, this should be a subset of Pn. Okay.
That is that the topology generated by all this? Each UI will have a topology now.
Yes.
Because of these maps.
Right.
Now to give a topology on Pn using these, you mean that is the topology generated by all this? Taking all.
Yeah, you can, so it's a fact, you can take the topology generated by this, or so okay, so thank you for pointing out this should have been subset not equal to, of course. So when I said that that there is a topology on each UI that makes Phi a homeomorphism, and then you all these topologies put together give a topology on Pn, I mean the following thing: a subset of Pn is defined to be closed or open if its intersection with each UI is respectively closed or open. That is the definition, and for this definition to work, a subset of UI intersection Uj is closed in UI only if and only if it is closed in Uj, and is open in UI if and only if it is open in Uj. That is the compatibility that you will have to check. So the topology on Pn that I want to give by gluing the topologies on the UI is the following: you define a subset of Pn to be closed respectively open if its intersection with this cover is closed respectively open. In particular, these UIs themselves will become open, because if you take the set UI, you will have to check that UI intersection Uj is open in Uj, okay, for every j different from I, and UI intersection Ui is Ui, and that is of course open in Ui. So each of the UIs by this definition will automatically become open subsets, and then you are only requiring that a subset of the ambient space is closed respectively open if and only if that if its intersection with respect to this cover is relatively closed or relatively open. So that is the topology that you can get by gluing the topologies on each UI. Okay. Now the fact I want to make is that each phi is an isomorphism of varieties, alright, and how does one do this? You'll have to show that phi, you have to show that phi is a morphism, you have to show that phi inverse is a morphism. So so let me do that properly. So what we will do is so we will have to what I am trying to say is that the phi's are isomorphisms, so I am trying to say that each UI is isomorphic to an, but of course each of these UIs is a quasi-affine variety because it is an open subset of a projective variety. Okay, so sorry, quasi-projective variety because it is an open subset of a projective variety. Okay, and I am just saying that these quasi-projective varieties are actually affine because they are isomorphic to affine these affine varieties. Namely, I am just saying that this natural open cover of quasi-projective varieties is actually isomorphic to so many copies of affine space. Okay, and then so so the way to check it is that you do the following thing: you use this lemma which I have stated earlier. The lemma is a map zeta from x to y, where x is any variety and y is an affine variety, in say an in am with coordinate functions x1, or let me put t1 etc. tm, is a morphism if and only if it pulls back each coordinate function Ti to a regular function on X. Okay, so this is a fact that we have already seen. I mean, we saw this in the context of affine varieties or quasi-affine varieties, but you can go and check that the proof has got nothing to do with the source variety being affine or quasi-affine. It could have very well been projective or quasi-projective. So the idea is, if you are just given a set theoretic map, okay, when do you check its homomorphism? I mean, how do you check its homomorphism? When is it a morphism? It's a very important, it's a very powerful lemma, but it's very easy, okay, and it's very easy to use. The proof is also easy, but it's a very powerful lemma, because if you want to check something is a morphism, you have to check two things. You have to check it's continuous, number one, then you have to check that it pulls back regular functions to regular functions. So checking involves two steps, but this lemma tells you that you can do away with that and do it in one go by just simply saying that if your target is an affine variety, okay, and your map pulls back coordinate functions to regular functions, then it is a morphism, okay. So if you use this lemma, it's very clear that it's very easy to see that phi and phi inverse are morphisms, and since they are inverses, set theoretic inverses of each other, it will follow that phi is an isomorphism, okay. So for example, if you try to apply it, so I try to apply this lemma to phi, my source variety is ui, which is a quasi-projective variety, and the target variety is an affine variety, it's just affine space, okay. And if I take if I take a coordinate function on this and compose with this, what I will just get, so for example, suppose I take the first coordinate function, will be if I take the coordinates here as t1 through tn, okay, then if I composed let us say t1 with phi, I will simply get this x0 through xn homogeneous coordinates going to x0 by xy, okay, and if I compose it with tj, it will be just this x0 through xn going to xj by xy, and xj by xi is of course a regular function on the source projective space, because it's a quotient of two homogeneous polynomials of the same degree 1, and it is defined on the set. I am dividing by xi is correct because I am on ui where xi is not 0, therefore it's very trivial to see that the pullback of the coordinate functions are regular functions, so that makes phi a morphism, alright. And similarly, if you go in this direction also, okay, so you can go in one direction because this is affine and this is any variety, okay. So for showing that the map is a morphism in the other direction, I will need to do something more. So let me write this down. Let me write that down. So proof of fact, let t1 etc tn be coordinates on coordinate functions on the target an, then if I look at the pullback, then their pullbacks by phi are the functions well t0 by I mean x naught by xi, x1 by xi and xn by xi, omitting xi by xi, okay, which are regular on ui. Therefore, by the lemma each phi is a morphism. So phi is a morphism by the lemma. Okay. Now so what this will tell you is that phi is a bijective bicontinuous morphism, but even that is not enough to ensure that phi is an isomorphism, because in the category of varieties the problem is that you can have a bijective map which is a morphism in one direction. It could even be continuous in the other direction, but it may fail to be a morphism in the other direction. So you will have to do something to say that phi inverse is also a morphism, okay, and for that of course to check that phi inverse is a morphism I cannot apply this lemma, because the target now is ui and I do not know for sure that ui is an affine variety. To start with, I do not know that ui is an affine variety, it is only a quasi projective variety. I cannot apply the lemma to show that phi inverse is a morphism. So I will have to prove phi inverse is a morphism, I will have to do it the hard way, namely I have to check it is continuous, and then I have to check that it is it pulls back regular functions to regular functions. Now continuity is something that I have already asked you to check, but it is probably easy to write down. So phi inverse is a morphism, that phi inverse is a morphism needs to be done, needs to be shown, cannot use the lemma, because the target is ui and I do not know ui is affine. But of course once I prove this fact it will follow that ui is isomorphic to an affine variety and therefore ui will become affine, but I cannot assume it when I try to prove it, okay. So so phi inverse is continuous because you know how will I show that it is continuous. So you know I start with to show it is continuous I have to show that if I take a closed set here its inverse image under phi inverse, which is the same as its image under phi, is a closed set in an. So I will just have to show that phi is a closed map or an open map, okay. So because phi is a closed map, equivalently open map, and why is phi a closed map? The idea is very simple. If you take a closed subset here, okay, that closed subset is the closed subset in the projective space intersect with ui because that is the induced topology. Now since it is a closed if you take its closure in, if you take a closed subset here and take its closure in the projective space, you will get a closure, you will get a closed subset of projective space. So it is the zero set of a homogeneous ideal, okay. Now what you do is you take all those elements in the homogeneous ideal and then just dehomogenize them in terms of these coordinates, okay. You will get an ideal here and it is the zero set of this ideal which is the image of that closed set, okay. So let me write this down. So what you must understand is okay, so that gives me an opportunity to say something. What is the algebraic translation of this morphism? The algebraic translation is, of course, the algebraic part here is the ring of it's a polynomial ring, it's the ring of regular functions on an, is the polynomials in T1 etc. Tn, okay. And what's happening here, the fact is the regular functions here are just it is just this polynomial ring localized at xi okay, that means you invert xi, but then after you invert xi it's still graded, okay, because you have inverted a homogeneous element, and then you take this degree 0 part of that will give you a subring, and that is the ring of regular functions in UI, okay. So the fact is that this map induces an isomorphism of these rings, and that is the geometric translation, that is the algebraic translation of the fact that this map is an isomorphism of varieties, okay. So let me explain that. So what you do is let f in U UI be closed, be a closed set. So f bar in Pn, this is the ambient projective space in which UI is sitting, is closed, which means f bar is the 0 set in Pn of I, a homogeneous ideal, okay. And now what you do is that so take define a map from the affine coordinate ring of An, which is k T1 etc. Tn to the set of homogeneous elements in H. This is just union of SD d greater than or equal to 0. And what is this map? So this map here is homogenization. So this is the homogenization map, and what is the homogenization map? If you give me a polynomial in T1 etc. Tn, okay, then this polynomial in T1 etc. Tn has a certainly it has a maximal degree, okay. Now what you, but this has only n variables, so what you do is that you homogenize it, namely you make every monomial equal, you make the degree of every monomial appearing in this polynomial to be equal to this highest degree by adding as many the required power of a new variable, okay, and that is a new homogenizing variable that you introduce, okay. And so the homogenization is, I put x I power degree f f of x naught by xi and so on xn by xi, okay. This is the homogenization process. So what you do is that if you do it like this, you must realize that when I write f of, when I plug in for T1 through Tn the x0 by xi, x1 by xi and so on up to xn by xi, of course omitting xi by xi, okay, then I will get a polynomial which will have the xi's in the denominator, okay. I will get a polynomial in the xi by xj, I mean rather polynomial in the xj by xi where j varies and I is fixed, but then by multiplying it by xi to the degree f I clear all the denominators, okay. So what you must understand is that this polynomial is an homogeneous polynomial of degree equal to degree of f, okay. So this method, this is called homogenization, alright, and there is a map like in this direction which is called dehomogenization. So there is a map called dehomogenization, and that's very simple. You give me a polynomial g x naught etc. xn, and I do the obvious thing. I simply send it to g x naught etc. g t naught, I mean g t1 etc. I put 1 where I have pi, then I put tn. Okay, so this is called dehomogenization. So what you do is there are these variables x0 through xn. Okay, now for xi you put 1. Okay, if you put 1 for the xi, then you get the remaining polynomial is only a polynomial in x0 through xn without xi, so it's only n variables, and these for these n variables you put t1 through tn in that order. Okay, this is called dehomogenization, and the fact is that, let me call this as f sub h, the subscript h being homogenization, and let me call this as g sub dh, which means the dehomogenization. Okay, instead of giving names to these maps, so any f which is a polynomial in the ti's is homogenized to give an fh which is a homogeneous polynomial in the xi's. Conversely, you start with a homogeneous polynomial in the xi's, you can dehomogenize it to give g sub dh is inhomogeneous polynomial, not necessarily a homogeneous polynomial in the ti's. Okay, so so you have this map, and the reason I have this map is because you can now check. It's a very simple set theoretic exercise to check that, you know, so I have now, see, I am trying to check that this map phi is closed. Okay, so I started with an f which is closed here, and I took its closure in the full space, and this f closure is the 0 set of an ideal. It's a homogeneous ideal. So now what I'm going to do is I'm simply going to take, since it's a homogeneous ideal, it's generated by homogeneous elements. Alright, so what I'm going to do is I'm going to take those homogeneous elements and I'm going to just dehomogenize it. Okay, so essentially what I'm doing is, see, the map is only from the homogeneous elements to the homogeneous elements. So what you do is this ideal breaks up into a direct sum of its homogeneous pieces, and so the ideal is equal to I intersection SD, a direct sum of I intersection SDs, and each I intersection SD is a subset here, and I take its image there. Okay, so I is direct sum I intersection SD, d greater than or equal to 0. This is because I is homogeneous. Okay, and consider I dh, which is definition is summation of I intersection SD. See, mind you, I intersection SD is this, I intersection SD is sitting inside SD, which is sub of SH. These are homogeneous elements, and on SH I have this dehomogenization map. Okay, so what I do is I simply take I intersection SD and I dehomogenize it. Okay, and then I take the sum. Okay, let me for safety take the ideal generated by that. Alright, and the fact is, so this bracket is supposed to mean ideal generated by this. Alright, and the fact now is that the image of this f under this phi is, I have to verify it's a closed set, and what is a closed set? It's just the closed set of this ideal. Mind you, this ideal is an ideal in on the left side, it's an ideal in A in K T1 etc. Tn. This is an ideal. Okay, this is an ideal there, and so it defines a closed set, and the fact is, what is that closed set? That closed set is actually the image under f, the image under phi of f. So fact is z of I dh is equal to phi of f, which shows that phi is closed. Okay, phi I of f showing phi is closed. and since I have written down all this, it's also easy to say why phi inverse is closed, and phi inverse is also closed is also easy to check in the same way. What I'll have to do is that, which I'll have to start with a closed set here and show its image under phi inverse is a closed set there. And what will I do? It's very simple. A closed set here is given by an ideal, it's given by an ideal in T1 etc. Tn, and then I take this ideal in T1 etc. Tn and simply homogenize it. I will get an ideal, I will get a homogeneous ideal, and the zero set of that homogeneous ideal is going to give me a closed subset of Pn. If I intersect it with Ui, that is going to be the image of this closed set under phi inverse, and that's how you check that phi inverse is closed. Okay, so let me write that also. So this is something that you can check. Okay, so instead of saying fact I should say check. Similarly, if z in, so mind you this z is in An, this z is a zero set in An. So similarly, if z in An of j is a closed subset of An for an ideal j in K T1 etc. Tn, then phi inverse of z An K j is simply z of this z in Pn of the homogenization of j, which is jh. Okay, is the homogenization of this ideal, and it is that intersection with Ui, showing phi inverse closed, that is phi is continuous. Okay, so so once you understand this homogenization dehomogenization, you see clearly that that's what is going on at the algebraic level. In fact, to be more precise, what is happening is that once this fact has been proved, what it is going to say is that Ui is isomorphic to each Ui is isomorphic to An as an affine variety. Therefore, you expect that the ring of regular functions on Ui is the same as polynomial ring in n variables. Okay, so that should give you some ring isomorphism, and you should have a nice ring description here. Okay, that also can be checked. So, but before I do that, let me complete the proof of this fact. I needed to check that phi inverse is a morphism. I have already checked that phi inverse is continuous. I will have to only check that phi inverse pulls back regular functions to regular functions. So it remains to show that phi inverse pulls back regular functions to regular functions and that would make phi inverse a morphism, and that together with the fact that phi is a morphism will tell you that phi is an isomorphism. So what should I do? So I have to show that this map pulls back regular functions to regular functions. So I should take a regular function here, I should compose it with this map and show that the resulting function here is regular. So that's also easily written in terms of the dehomogenization map. Okay, so start with regular function let me make sure that I am not messing up some notation. start with a regular function g by h on an open subset of ui, namely ui intersection projective space minus the 0 set in projective space of H. Okay. So you know a regular function on a quasi projective variety or projective variety is just a quotient of homogeneous polynomials of the same degree. So I start with a regular function g by h on an open subset of this, okay, where g h are homogeneous of the same degree, say g comma h are in some degree d part, okay, d of course I will assume now what you have is you look at, so look at then phi I inverse of g by h, okay. So this is a rather confusing notation. So you know I wanted to go back and look at this diagram. Phi I inverse is in this direction, okay. My regular function g by h is here, it's defined on this. I compose it with phi I inverse, okay, then I get the pullback. So so this means this simply means that you first apply phi I inverse and then apply g by h, and if you write it out is the function if you give me a point with coordinates t1 etc tn, what I am supposed to do is I am supposed to apply phi I am supposed to apply phi inverse to it. So the point to which it will go is it's going to be t1 dot 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 1 tn. These are the homogeneous coordinates where this 1 is in the ith position. This is the map which is phi inverse, okay, and then what I am going to do is I am going to apply g by h to this, okay, and so what I will get is I will get g of t1 etc 1 and tn by h of t1 1 tn, okay, this is what I will get. But what is g of t1 but g of t1, if I put g of t1 etc tn with 1 in the tith position, then this is a dehomogenization of g high of g. So this is actually, so what this tells you is that phi I inverse of g mod h is nothing but the dehomogenization of g by the dehomogenization of h, which is of course regular, which is regular on d of h dh. So I am done. So I am just saying that I mean this is if you write it down it seems a little complicated, but it is not, it's quite straightforward. I am just saying that if you give me a regular function here which is a quotient of polynomials, okay, if I pull it back, the function that I get here is simply the same quotient of not the same polynomials but the corresponding dehomogenized polynomials. But since it is again a quotient of polynomials, it is a regular function on affine space, because regular function on affine space is supposed to be defined by locally by a quotient of polynomials. So it's pulling back regular functions to phi inverse is certainly pulling back regular functions to regular functions, and what's helping is this language of homogenization and dehomogenization. Okay, so that completes the proof of the fact that phi I is an isomorphism. Okay, so so that completes the proof of this fact, and then let me also tell you, once this is done, so let me add one line to this. Okay, the pullback via phi I induces an isomorphism induces a K-algebra isomorphism from the regular functions on ui, which is the following. You take this this polynomial ring in n+1 variables, the homogeneous coordinate ring of a projective space. You localize it at xi. S sub xi is the localization of xi. Okay, and then you take its degree 0 part. Okay, see, localizing xi means you are inverting xi, so any element in the localization will look like a polynomial by a power of xi. Now for such a polynomial, for such a quotient, namely a polynomial by a power of xi, you can define degree to be the degree of the numerator polynomial minus the degree of the power minus the power of the xi that is occurring in the denominator. With this degree definition, you can check that the localization S sub xi is also a graded ring, and you take its degree 0 part. Okay, that will be a K algebra. That K algebra is exactly this. That is exactly the ring of regular functions on ui. Okay, and so in other words, I am just saying the regular functions on this ui are simply quotients of, they are globally given by quotients of polynomials, with the numerator polynomial being a homogeneous polynomial, the denominator polynomial being a power of xi whose power is equal to the homogeneous degree of the numerator polynomial. So the only regular functions on this ui, global regular functions, are the form g by xi power n, g by xi power t, okay, where t is the degree of g. They are the only global regular functions on this, and that is what you get when you take the this homogeneous coordinate ring, localize at xi, namely invert xi, and then take the degree 0 part for the induced gradation. Okay, and this you will get an isomorphism of this K algebra with the affine coordinate ring of affine space. This is what pullback of regular functions will induce an isomorphism from the ring of regular functions here to the ring of regular functions here. Okay, and that is described like this. Okay, and you can check this, you can check this equality. Okay, it involves a little bit of diligent checking that the global regular functions on ui is given by this ring, and you can also check that this map this map which is given by the pulling back of regular functions from the okay, I think my directions are wrong. If I want to use phi I, then I must pull back regular functions from here to here, so my directions are wrong. So maybe what I should say is I should rather change this to phi I inverse, or if I want to use phi I should change this. So let me change it, and phi I induces a K algebra isomorphism from A of a n to the regular functions on ui, which is S localized at xi, and you take this degree 0 part. So this is the so the fact is so let me repeat it. not only is each phi an isomorphism, but once you know phi is an isomorphism, I am just saying that the variety ui, which originally was a quasi-projective variety, is actually isomorphic to an affine variety. Because it is isomorphic to this an, it is in fact an affine space, and you know that whenever you have an isomorphism of affine varieties, it has to induce an isomorphism of the corresponding regular functions, and therefore this isomorphism by pullback should give me an isomorphism of regular functions here to the regular functions here. The regular functions here are just the polynomials in n variables, and the regular functions on ui are, you can check exactly the homogeneous localization of this graded ring with respect to xi, which means you localize with respect to xi and take the degree 0 part, which means you are taking quotients of the form homogeneous polynomial of certain degree by xi to that degree as a raised as a power, okay, and you get an isomorphism like this, right. And this map is also described in terms of this map and its inverse, as you can check, is also described in terms of homogenization and dehomogenization. You can write it down, right. So with that I will stop.